All right, welcome to the F-Star pop-up seminar. It's my great pleasure to welcome Sheera Shamsu to today's seminar. Sheera is a PhD student at IIT Madras and has been doing some really interesting work on verifying an OCaml-style implementation of a garbage collector in F-Star and Low-Star. And I'm really excited to hear about it today. So thank you, Sheera. It's all yours.
Yeah, welcome. Yeah. Hi all. Thank you for joining. So today I am going to present about a part of my PhD work, which is about mechanized verification of an OCaml-style garbage collector. So it's a joint work with Dr. Karthik Nagar, Dr. K.C. Shivaramakrishnan, Dr. Karthikeyan Bhargavan, and Deebesh Kafle. So this is a short speaker bio. So I'm Sheera Shamsu. I'm PhD student at IIT Madras and as well as an assistant professor at a TKM College of Engineering, which is a government-aided and autonomous college in India. And I actually started this project with zero knowledge in F-Star and not so good knowledge in formal verification. I was really excited about functional programming and fascinated about graph problems and formal logic. But our target was to get a verified and efficient GC for OCaml in 3 years. The trip was really steep, but actually with the help of my advisors and my technical collaborators, we have made significant progress towards our goal, and the project is still ongoing. Okay, so with that, let us start the introduction about garbage collector. So heap memory can be managed in 2 ways, either manual memory or automatic memory management. So as we all know, manual memory management can be done using malloc and free, whereas automatic memory management can be done using a custom allocator and a garbage collector. A garbage collector is functionally equivalent to the free of a manual memory management. So the languages which uses manual memory management are C, C++, whereas OCaml Java uses automatic memory management. So this manual memory management has issues, that is, it is error prone, it can cause memory bugs, whereas automatic memory management can be made free of memory bugs if it is verified formally. So why GC is important? So this is a statistics about some Chromium project bugs, blockchain bugs and all. The usual culprit of such memory management bugs are due to manual memory management. So in order to provide memory safety, we need a garbage collector. So now comes the question, why GC verification is important? Okay, so the answer is, if a GC is not verified properly, or an incorrect GC actually can produce same memory safety issues as that of a manual memory management. So in order to say a GC is correct, it has to preserve 2 properties. One is called GC safety. That means GC safety says that GC should free only dead allocated objects. Dead allocated objects means which are unreachable from program variables. And GC safety actually implies memory safety. Now GC liveness. So GC liveness says that GC should free all dead allocated objects eventually. So with these 2 properties in place, if we properly verify these 2 properties, we can say that GC does not alter or GC does not cause any memory safety bugs. But GC verification is not something new. So what we have done differently here? Okay, so our strategy to address the problem is, we have actually developed a specification and verification framework for GCs, which operates on OCaml-style objects. So this is the first work which actually targets OCaml's GC, or rather I will say it targets OCaml-style objects, which is compatible with a heap, compatible with OCaml. So a novelty here is our correctness specifications are based on graph reachability. So this is different from previous work, because most of the previous work, or almost I will say all of the previous work, define the GC correctness based on GC algorithm specific things. For example, mark and zip GC. they specify the correctness criteria based on some coloring invariants, not using graph reachability. So we tried to bring in textbook kind of correctness specification into our GC verification. And it also permits evolution of GCs rather than rewriting the correctness specifications always. So using our framework, we have verified a stop-the-well mark and zip GC, which is compatible with OCaml, and its performance is on par with an unverified stop-the-well mark and zip GC. And we have done our proof-oriented development in F-star, low-star to facilitate C code extraction. Why? Because why we need C code is because OCaml runtime expects the GC to be written in C. So we need a C code extraction. So these are the new features of our GC verification compared to prior works. Now we need to get some understanding about mark and zip GC algorithm and OCaml object layout. So this is a tricolor mark and zip GC stages. So actually, if we think about garbage collection is intuitively a graph search problem. Okay, it's a graph problem actually. So where the graph comes from? So the graph comes from the heap. Graph comes from the heap and the allocated objects in the heap. All the allocated objects and their interconnections forms the graph actually. So, for understanding what mark does, or what mark and zip GC does, let us see these figures. Okay, so what mark basically does is it uses a mark stack, and mark runs until the mark stack is empty. So during each invocation of mark in that loop body, what mark does is it pops out the top of the stack, and it colors it as black, and it pushes the unvisited successors of that particular object into the stack, and the operation of marking continues until the stack is empty. And see in the figure, if we see in the before mark figure, the root sets are pointing to A and D, and whichever objects which are pointed by the root set will be gray. Now, after the mark, we can see that all the reachable objects from the root sets are black. And after sweep, what happens is that sweep traverses from the lowest position of the heap to the highest position of the heap. And during its traversal, it checks whether the color of the object. And if it is black, it will turn it to white. And if it is white, it actually turn it to some color called blue, and it add it to a free list. So E and F are unreachable from the root. That's why they are added to the free list. So it has to be noted that mark implementation does not construct any particular graph like this, whereas mark verification does. Because our correctness specification is based on graph reachability, the verification has to construct a graph. We will see that. Now, OCaml-style objects. OCaml-style objects are like this. So, like every object will be having a header and a variable number of data fields. So, a header occupies one machine word, and each field occupies one machine word each. Now, this represents the bitwise division of the header value. So, for a 32-bit machine, the first 32 bits represents the object size. Object size means the number of fields which are following the header. The next 2 bits represents color, and the last 8 bits represent tag. Okay, so field values can be, so these are the field values. Field values can be either a pointer or an immediate integer. So how we will know whether it's a pointer or an immediate integer? If the LSB bit is 1, then it is an integer. Otherwise, it's a pointer. Now, for an object graph, the successors of an object. So here I am saying this is as object X. Its successors will be all the field pointers of that particular object. Now, in OCaml, there is a convention. An object is represented using its first field address. So, for example, here, the first field address will be represented as the ID of the object. So with that background, let us see how we have formalized our problem. So this is a heap. This is a heap example I have taken. So this is as I described the object layout, that such OCaml type of objects are laid out in the heap. So this is a heap. This heap is a byte addressable array, and we need to define something called a well-formedness property, which is needed for the GC to operate correctly. The well-formedness property says that all field pointers of all allocated objects should point to allocated objects only. So this is a mandatory condition. Without this, the GC will not operate correctly. Now, something called embed. We have defined something called embed. So here embed equal to 8 in this particular example. This is because this embed corresponds to the machine word of a 64-bit machine. Now array, for example, so say byte addressable array, right? So the array indices 0 to 7 actually represents the header part, this header part, and 8 to 15 actually are part of the first field of object 8. Now, let us see what is a OBJ set. Okay. Okay, there's a question, I think.
Sheera, just a quick question. On the header, you explained the object size and the color. What is the tag used for?
Okay, tag used for representing different types of objects. For example, there will be objects with no scan tag. So if an object has a no scan tag, so there is a value called 251, I think so. So if the value is greater than or equal to 251, then that object should not be, I'm thinking it is 251, I'm not sure. So if the value is greater than or equal to no scan tag, the GC will ignore such objects. So in our first work, so the work which I'm explaining today, we haven't made use of the tag. For the second work, actually, for the integration work, like our future work is like, which is ongoing. The ongoing work is actually to integrate with a real OCaml runtime. So there we are taking the tag into consideration. For this work, we haven't considered the tag.
Okay, thank you.
Yeah. So let us see what is an OBJ set. OBJ set of H. OBJ set of this particular heap H is all the white, gray, black, or blue objects. So the color bits are 2. That means we can represent 4 colors. So white, gray, black are actually representing allocated objects, and blue represents the free objects. And we need to understand that in this heap model, actually allocated objects and free objects are like they leave go together, like they leave together. So okay, so let us see what's so as I said, three represents the color. So this is this field is color, this field is the number of field size, row size, and this is the tag field. So a value of 3 represents a black block. Okay, one second. Okay, a value of 3 represents a black block. A value of 1 represents a white block. A value of 2 represents a gray block. A blue block is represented by 0. And then in this particular example, if we see the first field address is the ID of the object, then we can see that OBJs of H is actually 8, 32, 48, 72, and 88. It contains all colored objects. Now, what is allocs of H? So these are allocated objects, white, gray, or black. So from the current example, 8, 32, 48, and 88 are the white objects. The blue object is not there. Now, row size of header 8 equal to, so row size of header 8 means we need to go here and we need to see what is the size of this row size. So that is equal to 2. So that's the number of fields of field size in words. Now field pointers of 8H. So that means the field pointers of this object 8 in this heap H. So the field pointer is, first one is 48. So this is a, the LSB is 0. So it's a field pointer. So 48. Now next field is, from this row size, we can know that there are 2 fields following. So the 9 is actually in integer value because its LSB is 1. So it will not come into the field pointers. So now is pointer 16h. So this 16, value of 16 in h is actually 9. So this is not a pointer. So it will return false. It will check the LSB bit. Now let us see how we can construct a graph out of such a. So this graph construction is essential for doing the verification. So the allocs of H is 8, 32, 48, 88 from the previous example. Now vertex set of the graph. So graph is represented as G of H, which is represented by vertex edge pair. Now V equal to allocs of H. All the allocated objects will come into the vertex set. E equal to whatever their interconnection. So and it has to be in order. For example, 8 for 8 only one field pointer, so 48. For 48, there are two field pointers, but we need to see that for 48, the first field is 32 and the second field is 8. Both are field pointers. It should be added in the order they are seeing. So it should not be the case that 48, 8 will come first and then 48, 32. It should preserve the order in which they have been, they are present in the heap. So 48, 32. So this order preserving is very important for proving an important invariant property. Now successors of G of H of 48 means in the graph 48 successors. So 48 successors are 32 and 8. So since the E is ordered set, successors also will produce an ordered set. So now we need to see what is an accessibility relation. So accessibility relation is represented by this symbol. Okay, so in this graph, what is the accessibility relation? So 48 is accessible from 8, 32 is accessible from 48. Is there anything accessible? So essentially, every object itself is accessible. Like 8 accessible to itself, 48, 32, 88, all are accessible to itself. Also, 32 is also accessible from 8 through 48. This is actually the transitive accessibility or transitive reachability. Now we need to understand something called reachable subgraph. So reachable subgraph intuitively, so there are some formal definitions I have written here. So reachable subgraph intuitively is this. The set of, so in the allocated objects, there will be some allocated objects which are reachable from a root set, and there are some allocated objects which are not reachable from the objects. Okay, so this is a division actually. So the objects which are reachable from the root set, which are part of the allocated objects, are actually the vertex set of the reachable subgraph. So, so we know that the vertices of the graph is actually the allocated objects. So from the allocated objects, whichever is reachable from the root set will come into the reachable subgraphs vertex set, which is represented as VRG. And ERG is all their interconnections intact. So the edge, ERG consists of all the edges in E, which are actually the edges of the vertices which are present in VRG. So the edge set should be preserved. So this is a reachable subgraph. So let us run through an example. Suppose R list equal to 8. R list equal to 8 means the root set is actually 8, contains 8. And now V equal to 8, 32, 48, 88. Now, how we can construct VRG? So from 8, whatever is accessible, 8 accessible to itself, 48 and 32. These are accessible. So VRG will be constructed like this. Then what is ERG? ERG is actually like we need to see from 8, what are the edges in the edge set. So 8 outgoing edge is 48. That should comes into ERG. 32, there are no outgoing edges. For 48, 32 and 48, 8 are outgoing edges. So they should come into ERG. So this way we can construct a reachable subgraph. Now with this formal definitions,
let us... Sheera, sorry, one sec. Asim has a question.
Yes.
So my question is around this root set. Is it an input or like are there some indicators in the heap that what nodes are root set?
Yes. Yes. So like whatever is there in the root set, like the root set will be pointing to some objects in the heap. Those objects will be gray color in the heap. Their
No,
color will be gray.
how do we know is what is the like some how do we know some object some object is in the root set or not? Like what
Yeah, just if we see the color of the object, if its color is gray, then that will be part of the root set. No, it's not part of the root set. Actually, it is part of the stack. So, so your question is how we will. Can you please repeat once again?
I think the initial root set is the stack, Ashwin. Objects on the stack.
No, initially before mark starts, the root set is populated into the stack, and the corresponding objects are colored gray in the heap. So before mark proceeds or before mark starts, that's the initialization step actually.
Okay. I think I understand. Thanks.
Yeah, okay. So let us define GC correctness over graph, which is independent of the GC algorithm. Okay, so this GC correctness, this GC specification is for a stop-the-well GC. Like how we can use graph reachability to specify the GC correctness. So the initial heap is H0 and it's a well-formed heap. After GC, final heap is H1. Then the GC is correct if and only if the final heap is also well-formed heap. The final graph which is created out of H1 should be the reachable subgraph of H1, and the reachable subgraph of H1 is nothing but the reachable subgraph of H0. So I will explain one by one. Okay, so it has to preserve the well-formedness property. Is actually it is for memory safety. All allocated objects should still point to allocated blocks. Say their field pointer should not point to somewhere outside the heap or anything, or some junk values or anything. It should point to allocated blocks only, not to free blocks also. Now G of H1 equal to RG of H1 ensures that all garbage is gone. So whatever, finally after sweep, only white and blue blocks will be there. So the white blocks will be the allocated objects. So as I said in the first example, what sweep does, sweep colors all the reachable objects to white. Okay, so all the there are only blue and white object means only the white objects are the allocated objects. Okay, so in this way, all the garbage will be gone. So that this property ensures that. And RG of H1 equal to RG of H0 says that in the initial heap, whatever is reachable should still be reachable, and their interconnection should be preserved. That is what the third property is saying. So all of these three, actually the 2 and 3 together, one second. So 2 and 3 together implies that the reachable subgraph is preserved and all the garbage is gone. So this is actually ensuring that two properties of which I have said about GC correctness. So now let us switch to some extracted code. I will show. Okay, is it the screen visible now?
Yes, screen is.
Yeah. Okay. Okay. So so this is like I haven't like made it more formatted and all. Just raw extracted code. So this is our mark and sweep GC. So what there are three functions in mark and sweep GC. First function is actually root graying. So as I said now, that all the roots will be input. The root will be input to the GC. So the roots will be first populated into the stack, and the corresponding objects will be made gray in the heap. That is called root graying. Then mark proceeds, and then after mark sweep proceeds. So what mark does is this thing. So mark is actually like mark is actually a while loop which actually runs until the stack is empty, and it runs continuously some operations which I have made as mark heap body. So what mark does is it will pop out the top of the stack. It will make its color black, and it will find out its number of fields, and it will call something called darken. So darken, what darken does is, darken is another for loop. So it will scan the fields based on the, scan the fields from first field to till the last field. And it will see whether it's a pointer. If it's a pointer and if its color is white, then it will be pushed into the stack. Sweep or sweep I have explained. So the similar operations will be explained in the code also. I am just skipping that part. Okay. So so I have showed the code in order to understand that there are three parts for the mark and sweep GC. One is the root graying, second is the mark, and third is the sweep. So this is the correctness conditions for the how we can specify the correctness of root graying. So root graying takes as input a well-formed heap, and the precondition is that all the objects should be white or blue. So after this root graying happens, all the members of the R list should be part of the stack. And the stack, whatever stack we are taking as input for root graying will be an empty stack. So that empty stack will be filled with root set. The GC should be preserved only. The graph should be preserved between the pre-heap and the post-heap, because only coloring operation happens. There is no vertex set change, no edge set change. So the graph will be preserved, as well as the coloring also. We are changing the color from white to gray. When we add something to the stack, we are changing the color from white to gray. Both white and gray are part of the allocated objects. So the membership in the vertex set is not going to change because of the color change from white to gray. So that's why graph remains preserved. Now, the last property says that, so it is kind of tying up the gray nodes with the stack. So all the gray nodes in the heap can be found in the stack only, and only in the stack. So this kind of tying up is actually very necessary. This is the correctness for mark. So it will take as input the root grayed heap, that is the output of root graying function, and the resultant heap is say H2. So for the post condition, it should be well-formed heap. Also, the graph should be preserved. There should not be any alteration to the object structure of the graph. And the black objects in the heap are formed out of the reachable objects. So all the objects which are reachable from the root list should be black in the final heap, and the black objects are the only objects which are reachable from the root list. So this condition is actually blending the graph concept here with the algorithm concept, GC algorithm concept. Now, the final property is also very important, because we have tied up the gray color with the stack. So mark stops when the stack is empty. So what does that mean? There are no more gray objects in the heap. So this property is very essential, because no grays after mark, that means there are no dangling pointers, because if there are still gray, that means there are still unexplored objects. So sweep may free it. So this property is very important. And after that, so this is the sweep correctness. So after root graying, after mark, sweep comes into picture. So it's a sequential process. So sweep takes as input the heap from mark, and the resultant heap is H3. So sweep also should preserve well-formedness property, and the sweep actually ensures this correctness condition. That is the final graph. A final graph will be the reachable subgraph, and the reachable subgraph in the final heap is actually the reachable subgraph of the initial heap. I will show how we sweep can achieve this, and then finally, all the objects in the heap will be white or blue to make it ready for the next GC cycle. So this is the GC correctness we have defined with blending with algorithm specifics. So, we can see that there are some complexities involved in the verification, because there are three concerns happening in this specification. So first concern is, this is a graph reachability problem. And this is essentially a depth first search over a graph with cycles. Okay, so graph with cycles can cause a lot of issues, which we will see. And now that naturally, there are naturally enough concern with this particular problem, graph reachability problem. So we have created that as a layer 1. Now we have seen that the color change operations that is happening in mark, that is happening in mark is through a bitwise arithmetic, because the color is actually a bitwise value stored in the header. So bitwise alterations should happen. So that bitwise operation naturally forms a second layer. Now, finally, the mark implementation should be in C. So writing something in C is actually has its concrete memory requirements. Like we need to obey certain concrete memory properties, like fixed length buffers, like I should not overflow, buffer overflow should not happen. So there should be disjointness. So those kind of things are actually forms a layer 3. So these three things are intermingling in this problem. So graph reachability with bitwise arithmetic over a C implementation. So in order to handle the complexity associated with verification, we have decided to separate these layers, these concerns into 3 different layers. So this is our approach. So the topmost layer is the graph interface layer, where a DFS uses the graph interface to run DFS. Then in the second layer is actually implemented in F star. It's a recursive layer. Root grain, mark, and sweep is implemented in this layer in F star. And all the algebraic properties of the GC is proved in this layer, as well as the equivalence between mark and DFS is also proved in this layer. In this layer, the first layer, DFS layer, only focuses on the graph reachability proofs. And the final layer is implemented in Lostar. So the same root grain, mark, and sweep is implemented. But here they are iterative. They are implemented as iterative functions. And in the focus of this layer is to prove the output equivalence between, like, root grain is equal to root grain in F star, mark in Lostar is equal to mark in F star, like that. The output equivalence between F star and Lostar functions is the focus of this layer. And finally, the Lostar implementation using caramel comparer, we can extract to a verified efficient GC, stop the world GC. So how we have done this, let us see. So the verification, so the first verification focus is to prove the reachability. So for that, we have defined a reachability property inductively. So the reach is an inductive predicate which takes a graph as input and 2 vertices x and y. So there are 2 constructors, reach reflexive and reach trans. Reach reflexive says that every x is reachable to itself, and reach trans is described in this figure. So reach trans says that if z is reachable from x, then if z has an edge zy, then y is also reachable from x. So this is called reach transitive. So this definition I have pictorially explained here. Now, this is our depth first search. So depth first search is also like it takes as input a graph, a stack, a visitor set. A visitor set is needed because if the graph contains cycles, it can go into infinite loop. So in order to avoid infinite loop, whichever objects which are already visited will be added to the visited set. So so similar to mark, DFS also runs until the stack is empty. It will pop out the top of the stack. It will find the successors of that top of the stack, and it will insert the top of the stack into the visited set. And then the successors are actually scanned to see whether they are unvisited or not. Unvisited means if they are not present in stack and if they are not present in visited set. So both conditions. So if both they are not, both membership is not there, that means that is unvisited. Then such unvisited successors of such objects will be pushed into the stack. Like this, DFS continues. Now, there's a main correctness property associated with DFS. So for the reachability, this reachability property is very important. So so we need to see that DFS output a visited set. DFS output a visited set. So the output of DFS, so all the members of the output of the DFS, that means all the members of the output visited set are reachable from some root set, some object in the root set. And only the objects which are reachable from some root element should be present in the visited set. So it's an if and only if condition. So the DFS starts with a stack filled with roots, and then a stack filled with the roots similar to mark, and also it starts with an empty visited set. Now, proving the forward direction, it only requires establishment of an inductive invariant of DFS. That is, the contents of both stack and visited sets are always reachable from R. Okay, so if the contents of both visited set and stack are reachable, when the stack becomes empty, like whatever, like if we are able to maintain this invariant in the recursive procedure of DFS, we will be guaranteed that in the end, whatever contents in the visited sets are reachable objects. Now, the second direction is very tricky because the second direction says that all the reachable objects from the root set should be finally present in the visited set. So there are infinite paths. There could be infinite paths because of the existence of cycle. There could be infinite paths in that graph. And how we can guarantee that all the reachable objects from the root set are present in the visited set? Because this is the trickiness is caused by the particular nature of DFS, because DFS does not traverse every path in order to avoid cycle. Because whatever there in the visited set will not be traversed by the DFS. So DFS avoids certain path. So how we will guarantee in this condition? Since some paths are pruned away from the DFS, how we can guarantee that all paths are being explored, or either all the objects which are reachable through some such paths are added to the visited set? How we can guarantee that? For that, we need to come up with a lemma, because this kind of reasoning is quite difficult with deductive verifiers. So we need to come up with a lemma called shorter path, which says that if there exists a path Rxy between x and y, then there always exists a path R-xy that is guaranteed to not contain x. So this is true, because even if it's a cycle, we can remove the instant of x which is happening in that particular path, and then proceed from that. After removing that x, we can then proceed the path. So in that way, this is actually the cycle avoidance. So by careful cycle avoidance, we can now induct on the path length, and it's not infinite anymore. But this short path lemma is not actually sufficient to complete the proof of this backward direction, because we need to because of some other situation. That's what I'm going to explain. So we need to come up with two more invariants in order to complete the proof. The first invariant says that every vertex reachable from this R is actually root set. So every vertex which is reachable from R is either present in visited list, or there exists a vertex in ST or stack through which it is reachable. So that is actually a natural invariant, because what we are trying to prove is that all the reachable objects are either present in VL, or there is a vertex in the stack through which it is reachable. So when the stack is empty, the other condition will go away, and all the reachable object will be present in visited set will happen. So that comes naturally from the backward direction. But how the second condition will come up? So if the second condition is not there, some issue will happen. For example, that is what I have depicted in the figure. For example, suppose X I have popped out from the stack. Now Y is reachable from X. Now y is not in ST or in BL. Okay, now y need to be tracked. Okay, so naturally a successor z should be there for x through which y is reachable. Now suppose z is in ST. If z is already in stack, we are fine, we are done, because the DFS procedure can continue and it can eventually reach y. Suppose z is not in ST because z is already in visited list. What will happen? So in order to get to y, we need one more invariant. That's also a natural property of visited list. That is, every vertex reachable from any vertex in visited list is either present in visited list itself or it is reachable from a vertex present in ST. So without this invariant, this kind of conditions will not be, we will not be able to prove. So this detection of such invariants is very important to complete this proof, DFS reachability proof. So, so with that DFS reachability proof, so now our DFS is proved to collect all the reachable objects, and the visited list will be containing only the reachable objects. Now, let us see the verification of layer 2. So here in this, there are a lot of proofs. I'm not going into all.
Can I
Yes.
pause you for a second and ask a question?
Yes, sure.
You mentioned on the in the previous sequence that this kind of proof is hard to do in a deductive verifier.
Yes.
Can you say a bit more about that? What is the difficulty?
Because of this cycles, right? We need to, like, the natural path induction is not possible actually. Like we need to come up with this kind of like sophisticated lemmas in order to complete the proof. Otherwise, the cycles that exist in the graph can cause infinite loops. So we won't be able to do induction on that. And for example, like there was a previous work similar to this, like DFS reachability in Y3. I think it is formal proofs of tangents. It's a Y3 paper. So they also have mentioned in order to prove this backward reachability property, they have to make use of Coq. They can't do it in Y3. They were not able to do it in Y3. So this kind of proofs actually require this kind of invariance as well as lemmas, sophisticated lemmas to avoid such cycle. Like induction is not possible with when there is cycle.
I see. So maybe if I just to check my understanding, maybe what you're saying is that rather than doing this proof directly on the iterative code, the low star code, you're doing this proof at the level of the purely functional model, where you're not limited to just using deductive, Hoare-style verification. You can write lemmas, and is that the point?
Yes.
Okay. Thank you.
Yeah. So in the functional GC, I'm not going deep into the root graying or each of the small proofs. I'm not going deep into. I only focus on the most important proof. So the most important proof in this layer is the equivalence proof. That is how we can prove the equivalence between mark and DFS. Because we can see that mark operates on a linear heap and DFS operates on a graph. And they are operating on different data structures, and how we can prove they are equal, their operations are equal. So for that, we need to...
Just one question. So the heap type in this layer is defined as just an array of bytes or a sequence of bytes or something?
Yes.
Okay.
Yes. So mark operates on such a heap, and DFS operates on the graph V, comma E form actually. So, so the most...
Just 1 second, Sheera. Alex has a question in the chat. He says, what if we use distance matrices and use induction on those? I don't know if you want to elaborate, Alex.
Wait, do you guys hear me?
Yes.
Yes.
Okay, I mean, you spoke of complexity that is caused by infinite loops, possibly infinite loops, but I don't see how they could arise if you first store all the information on your graph in form of distance matrices. Because from what I have seen so far, we don't really care whether some vertex is reachable immediately from some other vertex, or it is reachable through few steps of recursion. And if we do not care whether it is reachable immediately or through some steps, why do we not use something like distance matrices and just forget about infinite loops? Like you will only have a matrix that will say whether the row element is reachable from the column element or vice versa.
So that will cause additional complexity, right? To store the distance matrix and all. Because our focus to make the GC is to don't do extra allocation or extra data structures. Only use the existing information.
So you're saying that building this matrix will be a lot of burden, like it will be
Yes.
computationally not very viable. Like,
Yeah, because our GC should be performant, right? So our aim is to only use the information or the facilities which are currently available with the object. So we just make use of the colors for that.
Okay, then never mind.
Yeah. Okay. So now this is very important. How we have proved the DFS mark equivalence. Like the DFS proof, this also is a little bit tricky. We need to be very careful while doing this proof. So what this proof says, what this theorem says actually, all the, like one mark finishes, it will output a heap. A resultant heap will be there. So all the black objects in that heap should be the objects in the visitor set produced by DFS, and all the members in the visitor set produced by the DFS should be black in mark. So they are tied together. Okay. So this proof. So this actually says that since DFS visited set is proved to be obeying the reachability property bidirectionally, this means that all the black objects created by mark are actually obeying the reachability property. So this ensures that mark is able to correctly mark all the reachable objects and only the reachable objects. So this theorem is very important. Now, in order to make this proof, what we have to do is that we need to tie up something. So here now there are membership check which is happening in DFS before stack and visited set, whereas color check happens for mark. So we need to dig up two important invariants. So these are the invariants. First invariant says that it's called stack invariant. Stack invariant says that all the gray objects in the heap and only the gray objects in the heap are present in the stack. And visited set invariant says that all the black objects in the heap and only the black objects in the heap will be present in the visited set. So as I said before, the mark happens in a heap where only gray objects, white objects, and blue objects are there. There are no black objects. And DFS also starts with an empty visited set. That means there are no black objects. So this invariant is satisfied trivially in the initial case. Going forward also, we need to ensure that mark as well as DFS is able to preserve these two invariants. So this preservance of invariance is necessary. Now, we can see that the last invariant, the visited set invariant, is actually nothing but an extended version. Like this visited set invariant can be extended to reach the proof of the final theorem. So what we have to do for this? What are the steps to prove this? So let us compare the DFS and the mark. Okay, so I have separated. So I have separated the DFS body and mark body from the recursive function for a purpose. The purpose is that I can separately verify their equivalence. In a recursive function, I need to use induction. So I want to avoid the intermingling of induction and the properties of each function. So that intermingling avoidance is done with the separation of body from the recursive function. So we can see that the stack which DFS. So we need to start with the same stack for DFS as well as the mark. Same stack should be taken. Okay, and the stack invariant and visited set invariant should also be preserved initially. And what DFS does, what mark does, they are identical actually. So X is popped from stack, X is popped from stack, the rest of the stack is X's, rest of the stack is X's. Now successors will be taken out from the success of X will be found out, and they are the X is inserted to visited set. So X is inserted to visited set is equivalent to saying X is colored black in H1, X is colored black. And now what we are going to do, the successors of X is actually pushed into the stack, which the success which are unvisited is pushed into the stack. Here, some function is called darken. So I said darken will push. I showed the code earlier in that the field pointers which are white in color will be pushed into the stack. So what are white color? What are white color? Like allocated objects are three colors: gray, white, and black. Black objects are in visited set. Gray objects are in stack. So what are white objects? White objects are basically unvisited objects. So that's why they are essentially, we can see that functionally they are doing the same thing. Now, how we will prove that? In order to prove that, first we need to prove that after the DFS body, the VL dash produced by the DFS body contains the same objects that are black in H2, like whatever darken produces. So whatever this mark body produces. So mark body produces only one black object in one invocation of mark, and that black object is actually added into the visited set in a DFS invocation. So we can actually prove this property. This property is not very tricky. Second property is prove that the graph is unaltered. So the graph is unaltered, as I said earlier, only the color change happening is from gray to black. Gray to black, and in the darken. So color header HX blacks means from gray to black. X is gray, X is turned to black. Now in darken, what is happening? All the white objects will be colored gray. So from white to gray. So these two coloring operations does not alter the membership in the object graph, because white, gray, and black are all actually members of the object set. So the membership is not altered. So that's why G of H equal to G of H2 we can actually prove. Since the member no field pointers are changed, only the colors are changed, and the membership is not altered with the color change.
Sheera, let me just give you
Yes.
a time warning or time check. Like we're getting close to the end of the hour. I think this is super interesting. So I think maybe, try to wrap up in say 7, 8 minutes.
Yes. I'm about to finish actually, only a few slides now.
Okay.
So the third property is very important. That is actually the stack equivalence property. So we have a stack which is going around, looping through these functions, right? So we need to prove that both stacks produced by push unvisited and stack produced by darken are actually equal. Equal means they are structurally equivalent. So here actually that edge construction of the graph comes handy, because I said edge construction should be an ordered set. So if the edge set is not ordered, we won't be able to prove that the stacks are actually structurally equal and their order is same. So this is a tricky proof. So in order to prove that, actually the hurdle is that push unvisited and darken operates on different lengths, because push the successors are actually pointers, field pointers already filtered out, whereas darken scans the entire fields which can contain integers also. They operate on different lengths. So in order to overcome that problem, we need a helper lemma which says that like if we start from a successor slice, a portion of the slice, and then do the push unlisted operation, and if we start from a portion of the field slice and then do the darken operation, they both eventually produce the same stack. If we are able to show this, if we are able to prove this invariant initially and during the operation and after the operation, we will be able to show that the stack equivalence can be maintained. So I'm not going elaborate into that lemma. Now, mark is a total function, so termination has to be ensured. For termination, I have used a property called the difference between set of allocated objects and set of black objects keep on diminishing. So we have to prove it using a proof by contradiction method. Now sweep verification, I'm just skipping. So I have added those things in slide. With sweep verification, actually, we will be able to prove that important property that the reachable subgraph is being preserved between initial and final heap. Now, I want to show how we have done the output equivalence of the last layer, that is the low star layer. So the issue with low star is that their unbounded buffers are unbounded sequences are available in F star world, whereas in imperative world, fixed length buffers are there. And every access requires anti-aliasing properties proof to in place buffer modification. And the challenge, one more challenge is that one is recursive and one is iterative. We need to prove that both of them produces the same result. Okay, so in order to ease the verification challenge, I made the recursive function tail recursive so that it corresponds to a loop kind of operation. So I made the recursive functions tail recursive. Now, this is a like low star terminology for those who doesn't know about low star. So this is a fixed length buffer. M0 is the memory state of the system. I represent a functional f of b of M0 means the sequence version of buffer, the functional version, that's the seq version of b in M0. And st top of 0 means it is used to store the top of the stack. So in this case, it is stored as 3. And SL-ST-M0 is actually the slice portion, the portion of the stack from 0 to stack top, because we need to pre-allocate fixed length buffers, so it can grow and shrink accordingly. So the important theorem here, we need to see here is that like how we can prove the output equivalence. So what we have to prove is that the heap which is produced after running, I have only shown a mark function. The heap which is produced after running mark in M1 is the final memory, is actually equal to the heap produced is functionally equivalent to the heap produced by recursive mark on the functional counterparts of the inputs. So, if it's a non-loopy function or non-recursive function, proving their equivalence is straightforward, because we only need to ensure the control flow and data flow. But if it is a loop-based function, for example, mark, darken, those are loop-based function, we need to come up with suitable loop invariant to prove that. So I just show how we can reduce the loop invariant. So this is the last function. So this is a darken function. I have keep them side by side. So this is the iterative version and this is a recursive version. So darken body can be straightforwardly verified because they doesn't have any loop or recursion. But whatever loop and recursion is there, the outer body, outer function, we need to come up with suitable invariant. So this way we can come like so darken will start from the first field so like this. So what will be a loop invariant in this case? So loop invariant comes from an intuition that the darken, like if you darken is like an accumulator function. Since it's a tail recursive function, it's an accumulative kind of function. So the loop invariant says that when you start darken from the functional equivalent of the initial heap and starts from the beginning of the field position, such a darken will produce the same output as that of running darken from any of the intermediate stages. So since the changes are accumulated into the heap in any of the intermediate stages, like for example, I is the loop variable. So in any of the intermediate stages, if you start darken, it will produce the same output. So this loop invariant is trivially true. It is true initially, and like we can prove that actually it holds during the loop body, and during termination also it holds. So like this, suitable loop invariants are needed for showing the output equivalence between low star iterative functions and F star recursive functions. So I have just made some diagrammatic representation how this is true. So this is iteration I. So whatever I have written, loop invariant is based on iteration I. So, and one more hurdle is there actually, because of fixed length buffers, low star require that the stack is actually can overflow, right? Stack is a fixed length buffer, but during the mark process, stack can overflow. So we had to make an optimization there, or rather I will say some kind of adjustment there. That is, we need to prove that stack will always have enough room to accommodate if at all a white object exists, because stack actually I made equal to the size of the heap. So all the objects in the heap are like, if any objects is white in the heap, that means that is not present in the stack. Since the stack size is equal to heap size, that means stack has enough room to push if there is a white object exists. So one more proof is required in order to overcome the fixed length buffer hurdle. So with that, actually, we were able to prove the output equivalence between low star GC and F star GC. And this is the benchmarking information. We have tested our things against a Bohem GC, an unverified GC, a partially verified GC, partially verified in the sense that sweep, this sweep is unverified and only mark is verified, and verified GC means sweep, mark, all those things are verified. So we got this kind of graph actually. The performance is almost equal. Only a slight issue with Bohem GC, because Bohem GC is conservative. And this is the statistics of the verification effort. And we have tested it out on binary tree benchmarks from computer language benchmarks. So this benchmark actually simulates the workload of a realistic program running on a GC. So that's why we have taken that. Now the ongoing work, the current work is actually integration of verified GC with OCaml runtime through GC feature enhancements. So as I said before, we haven't used a tag in this particular first work, which I have explained now. We need to use tag in order to integrate with the OCaml runtime. So like no scan tag, closure objects tag, infix tags, those kind of things we need to add in the tag area. And we need to suitably arrange the graph construction and the mark process accordingly with the tag intervention. So that work is ongoing. And now correctness spec is actually flexible enough to verify an incremental GC for OCaml also, because we can still write correctness specification based on graph reachability for an incremental GC. So we have conjectured that actually. And this is because some property called snapshot at the beginning property of OCaml GC that says that all the reachable objects at the beginning of GC should be reachable after the GC also. Because of this snapshot at the beginning property, actually we can extend or we can tweak the reachability property I have described for writing the correctness spec for an incremental GC for OCaml. And now that's all my presentation. So this is my sincere thanks to my guides, Dr. Karthik Nagar and Dr. K.C. Shivaramarshnan, for their correct guidance. I am very thankful to Dr. Karthikeyan sir for helping me with the Lostar tool usage, because I was not understanding how to use it. So he have guided correctly. And Deepesh for helping with the integration work, like testing out and writing a non-verified code for GC. So those kind of things, Deepesh actually helped. I'm very thankful for him. And I am thankful to Asim for giving me some initial guidance for using F-star. It was very helpful. And Imeric, I'm very much grateful. And Alex for resolving some of the queries related to F-star, seek usage and all. So I am grateful to these people. And thank you, Nick, for like inviting me to do an F-star seminar so that I can explain my work to people. And that's it. Thank you.
That was great. Thank you, Sheera. You've had a few questions, but I think we're a bit over time. But if folks have questions, any more questions that you can ask.
Yeah, I can answer if I know.
Like I said, I don't know whether it's a good idea or not, but I'd like to point out that we don't really need to build expensive, time expensive distance matrix. We don't need to build it actually, but we can use a ghost instance of this matrix and use proofs around such instance. And the equivalence of our marking system to such distance matrix. If that is ever a good idea, of course, I do not know if that's a good idea, but consider this as well.
So you mean to say, in order to avoid that DFS reachability proofs, we can construct such distance.
We don't need to construct. We don't need to construct it in runtime. But we can write a proof around this reachability matrix, but still keep it ghost. Like we can write a proof that if we were to construct such a matrix, then we will have all the properties we need. And then we prove that if we use our markings instead, it will be equivalent to using this distance matrix instead of our our markings. Do you understand what I say? What I mean?
Yes.
Like we prove things over very expensive and time-consuming structure of a distance matrix. And then we prove equivalence of distance matrices to our marking system, which is fast enough to be used in an actual garbage collector. And then we go back to showing that our garbage collector is correct because our marking system is equivalent to distance matrices. And we just proved that distance matrices are correct.
Okay, I see. Yeah, I'll think about it, Alex.
I have
but
one.
if that is for some reason not a good idea, just say so, because I'm not exactly deep in the topic and I cannot judge if that's actually a good idea.
So, okay. So, while doing this work, our idea was to, because in the GC handbook, textbooks and all of the previous papers, they have defined the GC correctness, at least in paper, based on graph reachability. Even though they used algorithm-specific things to prove the reachability. So, our aim was to bring in that notion directly into a mechanized proof. So that's why we haven't checked other possibilities. So we directly take that textbook convention and we try to see whether we can bring that. So, and naturally the reachability, this reachability things that can have many other uses also, right? So not only the garbage collection, like even for copying collection also, this kind of reachability helps. So that's why we thought of bringing a graph reachability into consideration rather than going into distance metrics. But however, I will think about it. Like, is there any advantage of doing that? I will think about it.
I have a question, Sheera. Like, in terms of your, modifying your development to account for these additional features that you were talking about, like incrementality or tags and so on. Do you feel like your development is amenable to such modifications, or while keeping everything working?
Yes, I already have added a certain tag related modifications, so it is amenable to do. So there was no hurdle. So far, I haven't seen any hurdle, and I am able to do the modifications. I can incorporate tags actually. So and I already have a theoretical model how we can do the tag based changes. So we don't need to explore, like, at least our first aim is to integrate with OCaml runtime, and that the minimal subset of features that is needed to integrate with OCaml runtime. So the minimal subset, whatever we have figured out, we can do actually with the current framework. We can actually change the current framework or tune the current framework. So mainly the mark algorithm, like mark process will change. It has to take tag into consideration. When mark changes, graph construction also changes, and the definition of well-formedness also changes. So if we are able to keep these three entities into sync, we will be able to do the verification. So I'm able to do certain changes related to tag in my current code. So I hope it will work, at least for the features which we have selected.
Great. Thank you so much. It's really exciting to see this work, and I'm really excited to see the. Sorry, was there another? If there's another question, I see. Maybe you have a question. I'm not sure.
No, I was just going to ask, like, what is the what are the chances of it getting into OCaml, for example? Like, if you add these tags, then can it get into OCaml in some form, like in some limited capacity or something? Is that the plan?
Yes, exactly. So our plan is to integrate with the OCaml runtime so that we can run certain OCaml programs on top of that. For doing the benchmarks, like we need to see, so it will be a stop the well GC. So we are not planning for incrementality as of now. Still with a stop the well GC, we want to add the minimal features which are required to integrate it with the runtime. That's the plan, so that we can run OCaml programs and we can run the standard tests which are part of the OCaml like repository.
That would be super amazing. I think this talk was great. I really enjoyed it. So thanks.
Yeah, thank you. And I'm also excited with that work. I also want to see the verified GC runs with a real OCaml runtime and what is the statistics of the programs.
Yeah.
But it's an amazing journey actually. A lot of hurdles was there because I didn't know F-star and how to use F-star, but through the journey actually I understood how to use F-star, and mostly I'm able to I need very little help now actually to operate with F-star and low-star, and it's very exciting actually.
Yeah, it's an amazing development. Just looking at the scale of what you've done, and dealing with all these everything from the low-level details of bit manipulation and object layouts to reasoning over these graphs and interesting termination metrics. And it's really very impressive. Thank you for sharing your work, and all the best for the next steps.
Yeah, thank you very much.
All right.
I will soon make the code publicly available also.
Great.
Yeah. Thank you.
Yeah. Thank you.
Bye.
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 Thank you all.